The purpose of this section is to estimate empirically the size of the market of a firm. Basically, you want to know if people in the neighborhood is gonna buy in one market or in some other market. The most basic way to estimate the size of a market is to use the Rayleigh's law of retail gravitation. The model postulates that an individual tendency to shop at a center A will increase as the size of the center increases and will decrease as the square of a distance between the customers and center A increases. If you have any knowledge of physics, you see that this is similar to the law of gravitation. Specifically, and that will be easier to see in an example, but let's read the definitions. The break-even point where trade is equally divided between two cities runs through a point where the ratio of the distances squared equals the population ratio. So the population of center A divided up by the population of center B equals the distance of center A square divided by the distance to center B square, where PI is population and DI is distance. Let's look at that more carefully. Here, I organize this information in an Excel file. This is city A and this is city B. The distance between the two cities is 100 miles. There is going to be a point here such as everybody to the left of this point will buy stuff in A, and everybody to the right of this point will buy stuff at city B. That's the idea. So the idea is I want to know the size of the market of a store in A, basically up to where is the market of a firm in A, and I want to know the size of the market of B, basically the area of influence of a firm in B. How am I going to do that? Again, this is what the model postulates. Those variables should be related where distance enters the equation squared, and this is the population ratio. Now, what I'm trying to determine is this distance here that I'm going to call dA. Basically, the limit of the market of influence here, the distance between here and here. dA is the variable I'm interested at, so dB is just going to be 100 miles, which is the total distance between the two places, minus dA. So dB, this distance here, is 100 minus dA. I substituted in here because I'm interested in calculating dA. That's going to be equal, according to the equation, according to the law of gravitation, PA divided by PB. Well, to simplify the equation, the first thing that I did is I took the square root of both sides. Taking the square root of both sides, the same thing as power half. And I did that to get rid of this exponent here, since this is the variable I'm trying to figure out. So I took the square root this side, then the square here disappeared. But on the other hand, I am assuming I'm taking the square root of this side as well, which is the same as power half. So I'm going to start solving this equation for dA. Let me copy this. Okay, that is going to be equal to population in A divided by the population in B and I'm going to take the square root of both sides. We can pass the denominator to the other side. What I'm gonna do now is multiply everybody here. That's gonna be plus Okay, so when I pass this to the other side, it's actually gonna be adding. So this will be actually plus 2.2. It's gonna be equal to this. So now I have to pass this dividing. It's gonna give me approximately 56 miles. Okay, so this point here is at 56 miles. Everybody up to here will buy in A. Therefore, this is more or less 44 miles since it's 100 minus 56. And everybody here in this region will buy in B. So that's another illustration of the result. So that's the size of the market of a firm in A, and that is the size of the market of a firm in B. Now this model has some shortcomings. The first one is the model implies a sharp break-even point. In reality, a central place's influence tapers off and hinterlands overlap. So usually instead of everybody up to here buying here and everybody up to here buying there is some overlap here between hinterlands. Another shortcoming, essentially distance reflects the cost of travel. Thus, the distance discount may be greater if travel is expensive or inconvenient. This is not taken into account in the model. Another shortcoming, people will travel farther for expensive goods, implying a smaller distance discount. Distance is treated the same. Now, some of these criticisms have been addressed by the development of a more sophisticated statement of Rayleigh law. We are going to see one of them. Basically, what we are going to calculate is the probability of an individual living at a region we are going to call I, shopping at a retail place located in a place we're going to denote S, which states by the subject center. Now Sj will be the size of the shopping place, J, that can be also S, and Tij will be the distance between other shopping centers J and places I expressed in time, and B, an S point, which could be like, for instance, square, as in the Rayleigh's law. And this symbol here, if you are not used to it, is summation over the places J. Now, again, let's do an example. We are going to assume that a developer is planning to construct a small neighborhood shopping strip of 10,000 square feet in census tract J. So here at J is where the shopping is going to be located. It is 10,000 square feet. There are two existing centers, A and B. this already exists, is 20,000 square feet, and this center already exists, is 15,000 square feet. And I'm going to calculate the probability or the likelihood that an individual located in census tract I will shop at the proposed center. Now the distance is measured in time, and it increases by 1 for each 5-minute distance increase as point has been determined to be 2. So this B2 is going to be 2, and in this case the distance is 4 because I'm measuring every 5 minutes, so 20 minutes divided by 5 is 4. The distance here is 6, so because I'm measuring every 5 minutes, I'm gonna count as 2, and 15 minutes I'm gonna count as 3, so I rounded up over here. Okay, so what's the probability that a person here in center I is gonna buy from here? Well, S is the size of the shopping place. Okay, in that case 10,000, so it's here. Tij is the distance which we're measuring in every 5 minutes, so in that case the book rounded up, so 2 units of 5 minutes, approximately 1 and a little bit, so we rounded up to 2 square. B, we decide it's going to be square. Now I'm going to divide by the summation of the same term but apply to every possible shopping place. So the first one is the same, we just calculated. We include it in the formula again since I'm summing for every shopping place. Then we're summing here B, 15,000 divided by 3 square, and then you're summing for this one 20,000 divided by 4 square. Add up everybody, divided this term by this, we get 0.46. How do we interpret this result? We may interpret the result as indicating the average shoppers in a location I will make 46% of their trip to the proposed center in J. So 46%, that's the probability of somebody here in I shopping here instead of here or here. Or you can also see it as the following: every time a person in I goes shopping, 46% of the time it will go shopping in the center in here, which is being constructed in J.